So in the last problem, we discussed population growing at a rate of 3.5%. Now, we do a lot of problems with interest also, and I think most of you probably understand that just like the banks don't wait till the end of the year to compound your interest, when you have something like population growth or population decline, it doesn't happen like all at once at the end of the year, or even all at once at the end of the month, or even every day. It's sort of a continuous thing. And so if you really want to get an understanding of growth and decline exponentially, you have to start understanding this concept of continuous. And what I want to show you is a little bit of well, a few, will get you to the use of E is what we're really working on. So let's look at this first function. The first time we did it was when we had a 3.5 percent increase every year, okay? And I'm going to go ahead and take that, and if we do that the first time, let's compare a few times, okay? We're going to compare like as if we just calculated it yearly. Why won't this grab? I don't know. Okay, there we go. So this is just if they compounded it yearly. Let's go all the way to that 50. And, figured it out that way. Now, let's take this one, and let's say this is going to be equal to, we're going to compound it monthly. 1.5 times 1 point, well, we're going to have to do this a little differently. 1 plus 0.035 divided by 12, okay, because we're going to get a 12th of that 3.5% each month, and we're going to compound it. We're going to calculate the growth 12 times as often. So we're going to put some parentheses and say 12 times this, and I'm going to close those parentheses. And again, well, something went wrong there. 1.5, oops, I forgot the little times sign in there. That should do it. Okay, so what happens when I take that function and I drag it down? It's pretty close, okay? We're going to increase the, you can see it's a little bit more, okay, but not very, very different. Well, let's go even further, okay? And we're going to say this is going to be equal to 1.5 times, let's compound it, let's pretend the population growth is figured out every day. So we're still going to use years as our t, so we're going to say 1 plus 0.035 divided by 365, because we're only going to take a 1/365th of that 3.5% per year, and we're going to raise it to, and I forgot my times sign again, we're going to raise it to the power of 365 times the year, the number of years that have passed. Okay, and obviously the first year's still going to be 0, because anything to the 0 power is 0. And let's see what that does. Now, all of a sudden, calculating it daily, which is pretty often, it doesn't change very much. It goes up a little bit, and there's a little bit, and a little bit, okay. Well, in reality, things don't happen that way. They go continuous. And so we're going to try this, we're going to try to explain that what happens is as we approach a continuous, as we get to this thing called E, and we're going to change this 1.5 times, and this time I'm going to say to E, I'm going to use an approximation for E of 2.718, and we're going to raise that to the power of the rate 0.035 times this, okay. Now this is a very different function than the others. All of a sudden I'm just using the rate, not 1 plus the rate. There's no 100%. There's just 1.5, which is the starting population, times E raised to the RT power. And we'll see what that does. And if you look, it's really not very different. but it is much more accurate in reality. And this works. You look at the minor differences between these two numbers. Looking at it on a graph now, I'm going to show you. I zoomed way out on this, but okay. I've got two functions graphed here. Okay, I have the original one. Let's take this one out. Okay, this is our original population graph, and I can even go. This is the x. Okay, this is our original population graph. Y equals f of x equals 1.5 times 1 plus 0.035 raised to the x power, and you can see as you zoom out. That this thing will spike just like anything else, any other exponential function. As time goes on, that thing will start growing faster and faster. Even though it's only 3.5% per year, it's going to get up there quickly. Now, what happens if instead of that I graph the e to the rt function? Okay, look how closely those things go. Okay, now if you go back to that line, when did it equal 4 million? It looks from here like, wow, practically exactly the same time. Well, in reality, if we zoom in close enough, you can see that it climbs a little faster with the continuous, and it actually ends up being almost a half a year earlier by our calculations that population would have reached 4 million. Now, to solve that mathematically, we would do a slightly different thing than the last time, okay? Because we started out with, again, we have this function, the population equals 1.5 times e to the 0.035 t, okay? And we want to know, when does that equal 4? So when does 4 equal 1.5 e to the 0.035 t? Now, again, we're going to divide both sides by 1.5, and we get 4 over 1.5 equals e to the 0.035 t. Now, look at this. Do you remember the natural log? Okay, what does this say to us? This says that ln, natural log of 4 over 1.5 equals 0.035 t. Now, all of a sudden, I've got, and I can divide both sides by 0.035, and I have a very simple calculation to do. Okay, I have 4 divided by 1.5, and I'm going to get that's equal to this. Okay, I'm going to take the natural log of that and divide it by 0.035, and guess what I have? My answer. Okay, so if you have a continuous growth or a continuous regression, it's really pretty simple to find out when things happened. I guess that's about it. Let's try a regression though. Let's say we got, no, let's just call it